Welcome to the Cosmic Classroom. Today we're going to be looking at the 2016 May Physics Paper 1, so let's get started. Question 1, we've got a sphere inside a cube. We're told the length of the cube and the diameter of the sphere are the same, with the same uncertainty on the measurement. What is the ratio of the percentage uncertainty of the volume of the sphere to the percentage uncertainty of the volume of the cube? Well, the volume of the sphere is 4/3 pi r cubed, and the volume of the cube is, since it's got equal dimension size, it's just the length cubed. Now, when we go from the diameter to the radius, the percentage uncertainty stays the same, since it's just a division by a constant. So we've got that the volume is dependent on the 10 centimetres cubed. The volume of the cube is also dependent on the 10 centimetres cubed, so both of them have the same percentage uncertainty, and both of them are raised to the same power, so the percentage uncertainty of both the volumes will be the same. The answer is B, or 1. The percentage uncertainties will be times by 3 for both, and it's the same percentage uncertainty because it's the same measurement. Question 2, got aircraft moving horizontally, parachuted leave the aircraft a few seconds later. Which graph shows the variation of the vertical speed? So not interested in horizontal velocity, just the vertical speed time t from the time she leaves until just before landing. Well, this is a terminal velocity question. Going to accelerate to terminal velocity during the free fall. Then when the parachute opens, there'll be a rapid deceleration and they'll reach a new lower terminal velocity with the parachute open, and the only graph that shows that is A, and that's actually a GCSE level question. We should be able to recognise that graph. We've got increasing velocity going towards a constant velocity, rapid decrease in velocity when the parachute opens, going towards a new lower terminal velocity with the parachute open. Question 3, object mass m rests on a horizontal plane. So we've got a horizontal plane, object of mass m. The angle that the plane makes with the horizontal is slowly increased from 0. When theta equals theta naught, the object begins to slide. So we've got an inclined plane question. So we're raising the angle, and when theta equals theta 0, the object begins to slide. What are the coefficients of static friction and the normal reaction force at that angle? So let's add on some forces to the diagram. We've got the weight to contend with, we've got the normal reaction force, and if we're just at the point of sliding, we've still got the mu static times n. Balancing the mg, we're just in that kind of transitionary phase where the weight acting down the slope is balanced by the static friction up the slope. You tip it any further, it's going to slide, and we have the normal reaction balancing the weight. Now, we should be familiar with the fact that the angle between the weight and the direction that is perpendicular to the slope is equal to the angle of the slope, so that is also theta naught. And now we can get some expressions for kind of our horizontal and vertical forces up and down the plane. So the normal reaction force is being balanced by a component of the weight, and that is mg cos theta naught to bring it round to balance n. And then in the, so that gives us straight away n is either A or D, not B or C. And then along the plane of the slope, we've got that the frictional force, mu Sn, is balancing the component of the weight down the slope, so mg sine theta naught. We can substitute in the expression for n above, so we can get mu s mg cos theta naught is mg sine theta naught. The mg's are going to cancel, rearrange that, mu s is then sine theta naught over cos theta naught, which is tan theta naught, so the answer is D. Question 4, so we've got a ball hitting a wall and rebounding. So this is a momentum style question. Rebounds with a speed slower than its initial speed. Duration of the collision is t. What's the magnitude of the force and the loss of kinetic energy? So we've got the ball coming in at speed u, impacting a wall, going away in the opposite direction with speed v. That speed is lower. It's in the opposite direction, so it is negative. It's negative v in the opposite direction. So first of all, let's consider the average force. So the force is the change in momentum with respect to time. The change in momentum is the initial momentum minus the final momentum, and this is where we get the minus, but then the final velocity is a negative. It's in the opposite direction, so we get a minus mv because of the direction change. Mu is to the right, mv is to the left, so it's negative. It's a vector over t, and that will simplify out to mu plus mv, and we can take the m out of that because the m is the same for both, so it's mu plus v over t. So that makes the answer A or B. We can get rid of C and D. So then we're after the loss of kinetic energy. So the loss of kinetic energy is going to be, it's going slower afterwards than it was before, so it's going to be the initial kinetic energy minus the final kinetic energy because it's going slower. Hopefully we can see we can take the half and the m out, and we get a u squared minus a v squared. So it's the square is inside the brackets, so the answer is A. Question 5, we've got a train on a straight horizontal track moving from rest at a constant acceleration. The horizontal forces are the force from the engine, and then a resistive force which increases with speed, which graph shows how the power developed by the engine changes with time. So if we think about what we've got going on, we've got the train. There is a resistive force acting against the train. There is the force from the engine acting. It has a constant acceleration, so it's always accelerating. So the force from the engine always needs to be larger than the resistive force in order for there to be a continual resultant force and therefore a continual constant acceleration. So as the resistive force increases, the force from the engine is also going to have to increase as well. Now we're after the power produced by the engine, so we should be familiar with this equation, that the power equals the force multiplied by the velocity. Now F is the force from the engine. So if we think about what's happening here, over time, the force from the engine is having to increase in order to maintain that resultant force as the resistive force increases, but the train is also constantly accelerating, so the speed is also increasing with respect to time. So both the force from the engine and the velocity are both increasing over time, therefore the power developed by the engine is also increasing over time. That means we can automatically get rid of A and C. It's then just a question of whether it's a linear increase or a non-linear increase. So if we think about what might be going on here, it is doubly increasing. So I can tell you the answer is D. Both quantities are increasing with respect to time, and when we multiply them together, we're going to get a non-linear increase for P. But just to prove that to you, if you can't quite see that, if we take some values, let's say every second the force from the engine increases by 1 Newton. And let's say each second the velocity, the speed of the train increases by 2 meters per second. So they can both increase linearly. That gives the power from the engine is the multiplication of those two numbers. So we've got 2, then 8, then 18. That is a non-linear increase. The answer is D. Question 6, we've got acceleration with respect to distance. What is the total work done on the object? Well, work done is force times distance. If we know the acceleration, we can work out the force from F equals ma, so we can work out the resultant force from F equals ma. So let's have a look at the graph. So between 0 and 15 seconds, we've got a constant acceleration, so a constant resultant force of, we're told the object is 3 kilograms, so we've got a constant resultant force of 3 times the acceleration is 20, so we've got a constant force of 60 newtons, which means the work done during the first 15 seconds is then force times distance, so 15 seconds, 15 meters, 0 to 15 meters, not 0 to 15 seconds, not reading the graph correctly. That is 900 joules done during the first 15 meters. We can then do the same for the second portion of the graph, so from 15 to 25 meters. Now, the acceleration is changing linearly, which means the acceleration is also changing linearly, and if it's a linear change, the average is half the maximum value, and we use that for our calculations. So the average resultant force during the second part of this graph is half the maximum, so the maximum is 20, half of that is 10, so it's still the 3, but now it's times the average acceleration, 10, so that is 30 newtons, and then the work done during that section is 30 times 10 is 300 joules. Add those two numbers together to get the total work done, that is 1200, the answer is C. Question 6, temperature time graph, changes of state, specific heat capacity. We've got 0.6 kilograms of liquid placed into heater. Specific heat of vaporization is 200 kilojoules per kilogram, so that's during this section of the graph, and then we're turning into a gas. What is the power of the heater? So the power is energy transferred with respect to time. So if we look at this graph, we can work out how long it takes for the substance to melt. We are told the specific latent heat of vaporization. The energy required to change state is the mass times the specific latent heat divided by the amount of time it takes. So the mass of the substance is 0.6 kilos. The specific latent heat is 200 kilojoules, so 200,000 joules, and that takes a grand total of 40 seconds. A little bit of mental arithmetic, that is 3,000 watts. The answer is B. Question 8, conditions of density and pressure for a real gas to be described are the equations of state for an ideal gas. So this is the definition of what an ideal gas is. So an ideal gas, the particles take up essentially none of the volume of the gas. So we need the volume of the gas to be significantly larger than the volume of the particles. So we need the gas to occupy a large amount of space, a large volume. We also need to be virtually no interparticle forces. So we need the particles to be really far apart so that we can take the interparticle forces as being 0. So we need the particles really far apart. We're going to get that with low density, so a large volume compared to the mass, and with low pressure. Again, we need the particles far apart. We're getting a lower pressure gas for a larger volume. So the answer is A, low density and low pressure. That is a knowledge question. Question 9, two polarizers. They are initially angled so that theta is 0. And we're asked which of the graphs represents the variation with theta of the intensity that we receive at the end here. We've initially got intensity I0. So what intensity are we getting at the end once we've gone through both polarizers? Well, let's consider the starting setup. So when theta is 0 degrees, the light is initially horizontally polarized. So at I0, it's horizontally polarized. The first filter is then also horizontal, so all of the light will pass through the first filter, polarizer P. But then the second polarizer, polarizer A, is vertically orientated. So A is vertically. None of the light at P is getting through A. So in the initial setup at 0 degrees, the received intensity is going to be nothing. We're not going to receive anything. So we scroll down to our graphs. That gets rid of A and D straight away. Okay, let's twist this round now to 45 degrees. So again, so theta now is 45 degrees. So again, initially the light is horizontally polarized. We now have the second filter, sorry, the first filter, filter P, polarizer P, at an angle, and then we have polarizer A in the vertical orientation still. Now, because P is at an angle, some of the light in the horizontal direction will be able to pass through that due to the vector nature of the transmission of the waves, the electromagnetic waves, and through the medium. Some of I0 will be able to pass through P. It's not completely at 90 degrees. So if the polarizers are not completely at 90 degrees, there will be a component of the vector that will be able to pass through. So some light will get through P. Then if some of the light has made it through P, it's the same argument. P is not completely at 90 degrees to A, therefore some of the light will be able to get through. So there will be some transmission. There will be some transmission through this orientation. The polarizers have to be at 90 degrees to each other for us to get absolutely no transmission at all in terms of the direction of their polarizations. So we're going to get some transmission at the 45 degree angle, and that therefore gets rid of C and gives us B, and that works because if we go around to 90 degrees, polarizer P is then at 90 degrees too, so polarizer P would be at 90 degrees to the direction of the initially polarized light, and we would get nothing through at the 90 degree angle. So that does tally with that graph. The answer is B. Question 10, standing waves in a pipe. We've got two pipes. We've got pipe L with two open ends. Frequency of the first harmonics of both pipes is the same. So first harmonic of our open pipe, node in the centre, antinodes at both ends. The length of that pipe is L. And then we've got one pipe closed at one end, open at the other end, first harmonic, node at the end, antinode at the opening, and the length of that pipe is L dash. For this first pipe, L is equal to half the wavelength, or twice L is equal to the wavelength of the wave in there. So the frequency in this pipe is V over 2L. Then in this second pipe, L dash is now equal to a quarter of the wavelength. So 4 times L dash is equal to the wavelength. The frequency is equal to V over 4 L dash. And we're comparing L dash over L. So rearrangement of that, L dash over L. So L dash is V over 4F. L is V over 2L. Flip and multiply the fraction on the bottom. V over 4F is equal to 2, oh, that's not come out like an F. 2F over V. Not an equal, we're multiplying. The V's are going to cancel, the F's are going to cancel, we're left with 2 over 4, or a half. The answer is D. Question 11. Ray of light passes from air into water. What are the change in wavelength and the change in angle? So it's very straightforward. This is a GCSE level question. So when we go from air to water, we go into a higher refractive index. The ray of light bends towards the normal because it has slowed down. So the angle has decreased. Therefore, A and B can go. The wavelength, so if we think about the V equals F lambda expression, frequency in refraction is constant. So the frequency is unchanged, but the reason that it refracts is that the speed of the wave changes. So when it goes into water, the speed drops. Therefore, to keep f constant, the wavelength must also drop, making the answer D. We've got a circuit, EMF 6 volts, no internal resistance. We've got two resistors, 4 ohms in parallel. The ammeter has a resistance of 1 ohm and the voltmeter is ideal. Now, if the resistance of the ammeter is 1 ohm, the ammeter is not an ideal ammeter, which basically means it's behaving like a little 1 ohm resistor in this circuit, which we will need to take into consideration. What are the readings of the ammeter and the voltmeter? So, what's the current flowing in the circuit? What's the voltage dropped across the 4 ohm parallel branches? So first thing, it's going to be some kind of V equals IR question. We need to know the total resistance of the circuit. So for these two resistors in parallel, we get 1 over 4 plus 1 over 4. So 1 over RP is 2 over 4. Flip the fraction on both sides, RP is then 4 over 2, so the parallel combination has a resistance of 2 ohms. The total resistance in the circuit is then that parallel combination plus the 1 ohm from the ammeter. It's behaving like a resistor. So the total resistance in the circuit is 3 ohms. That gives us the total current in the circuit, and therefore the current flowing through the ammeter, as the voltage divided by the EMF, so what we're getting from the cell, divided by the total resistance of the circuit, so we're getting 2 amps through the ammeter. So B and D can go. Then it's how much we're getting across the voltmeter. Well, essentially, this section here is behaving like a 2 ohm resistor. So we've got a 2 ohms and a 1 ohm sharing the voltage from the circuit. So we're going to get twice the voltage across the 2 ohm as we will across the 1 ohm, because the resistance is larger. It's still got to add up to 6. So we're going to get 4 volts across the parallel section, 2 volts across the ammeter. We can do that with maths. We can check that with maths. So we can do V of either the parallel section or the ammeter. But I can do the voltage across the ammeter as the 2 amps multiplied by the 1 ohm resistance it has. 2 volts goes to the ammeter. Then that voltage is shared with the parallel section, so V of the parallel section is equal to then the 6 volts minus the 2 volts across the ammeter is the 4 volts. So the answer is C. Question 10, got a wire carrying a current in a magnetic field. The direction of the field is out of the page. We've got the length of the wire, what's correct about the direction and magnitude of the force on the wire. So direction, you're going to need to get Fleming's left-hand rule out. Thumb in the direction of the force, index finger in the direction of the field out of the page, current in the direction shown in the diagram, kind of diagonally up to the top right. If you orientate your hand correctly, you should then find that your thumb points off in this direction, so that is the direction of the force, so C and D can go, it's A or B. Then the size of the force is given by this expression, BIL sine theta. Now the theta is to do with the angle between the field direction and the current direction. Now the field, it's going to be difficult to demonstrate here on a piece of paper, but the field is coming up out of the page and the current is going across the page. Now those two directions are at 90 degrees to each other. So if we're moving in a plane that's moving up out of the page at 90 degrees to the paper, and then horizontally across the paper, those two directions are 90 degrees. That makes theta 90 degrees, and sine theta is equal to 1. So the size of the force is equal to BIL. So the answer is A. Question 14, we've got a mass on the end of a rod, rotating at constant speed, performing circular motion. And we've got some statements. We've got to pick the one that kind of completes the sentence to make it correct. So the force exerted by the rod on the mass is 0 everywhere. I would hope that we would be happy to get rid of that instantly. We know when we rotate things in a circle that there needs to be some kind of force along the connector at certain points. We should also know that the size of that force varies depending on position. So it's definitely not constant in magnitude. For example, when we're down at the bottom here, we have the weight down, the force from the rod will be pulling the mass back up again. Our centripetal force must be constant throughout. When we're over on the side, the force from the rod is over here, and we've got the weight down. So in position A and position B, at position A, my centripetal force is equal to Fr minus mg. But then at position B, my centripetal force is equal to just Fr. The weight is in the vertical plane, not the horizontal plane, remembering that centripetal force always acts in towards the centre of the circle. And the two centripetal forces must be equal to each other. Therefore, the force from the rod is definitely not constant in magnitude. Now we get to C and D. The force from the rod is always directed towards the centre. It's a minimum at the top of the circular path. Now, this is a different setup to when we do this with a string. When we do this with a string, then we have tension in the string, which always acts in towards the centre of the circle, and we get a varying value for the tension. It ends up being a minimum up at the top because the weight acts down into the centre, meaning that the tension pulling in towards the centre doesn't need to be as large. But if we think about what we've got here, if we think about the scenario up at the top, we've got the mass on the end of the rod. Now this rod is rigid. So when we get to the top of the circle, we have the weight from the mass pushing down on the rod, but the rod does not collapse. So the mass pushes down on the rod, and the rod is therefore, because it's solid, going to push back up on the mass. It's going to push back up towards this, back upwards in the vertical direction, away from the centre of the circle. That's different to when we do this with a piece of string. So because the rod is solid, when we're up at the top, the mass pushes down on the rod, and the rod pushes back up on the mass. The force on the rod is away from the centre of the circle at the top of the loop, meaning that C is incorrect. But the force from the rod is a minimum up at the top. If we make this position C, my centripetal force is still constant, but now we've got mg minus the force from the rod in terms of our direction. So the force from the rod can be the smallest value there as we go around the top of the loop. So D is the correct answer. Simple model mass and 5 energy levels. What's the maximum number of different frequencies in the mission? So this is how many different transitions can you get. So 1, 2, 3, 4, 5 energy levels. You can draw this out really quickly. If we start at the top, we can go all the way down to the bottom. 1, we can go to the next. 2, 3, 4 different transitions there. If we start from 1 down, we get 1, 2, 3 transitions there. 1 down again, we get 1, 2 transitions, and then 1 transition at the end. That is a grand total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 transitions. The answer is C. There are 10 possible different frequencies we can get from the movement of the electrons in the energy levels. 16. 3 fundamental forces. Which one is in order of increasing strength? So there's a bit of knowledge required here. Gravity is the weakest of all the fundamental forces. The gravitational force is the weakest of all the fundamental forces. We've then got electromagnetic and the strong. So the strong, we've also got the weak nuclear force as well. The strong nuclear force is the strongest, and gravitational force is the weakest. It's then weak nuclear force, then electromagnetic, then the strong nuclear. The answer is C. It's the only one that starts with gravity as the lowest. Gravity's in the wrong position in A, B, and D. Question 17. Patterns in graphs. What can be deduced from a graph of neutron number versus proton number? So this shows us the belt of stability, the neutron number versus proton number graph, where if we look where an isotope sits, we can tell whether it's going to do beta minus, beta plus, or alpha decay, or possibly fission, depending on its position on the graph. If you're not sure which graph I'm on about, just Google belt of stability graph. This is the graph that we're plotting here with the neutron number versus proton number. It shows us the short range nature of the strong nuclear force because of how the different decays occur. It's not to do with binding energy per nucleon, that's a different graph. It doesn't tell us anything about quarks and leptons. It can indicate to us which particles will undergo alpha decay, but it doesn't give us the evidence for the existence of alpha decay, but it can show us which isotopes may well undergo alpha decay depending on their position, but not the existence of alpha decay. 18, solar panel, surface area 0.4 meters squared, efficiency 50%. We're getting 0.25 kilowatts per meter squared from the sun reaching the solar array. What's the average power output from 10 of these cells? 10 of these panels. So the total area we're dealing with is a 4 meter area. So the power received, so the power that's coming in to those 4 meters, the incoming power is 0.25 kilowatts per meter squared, and we're dealing with 4 meters worth able to receive, so we're getting 1 kilowatt coming in total. But then the panels are only working at a 50% efficiency, so of that 1 kilowatt they receive, they're only outputting 500 watts. 19, correct order of any transformations in a coal-fired power station. Again, this kind of GCSE level knowledge here. We should know that we start off with chemical energy in the coal. We're getting electrical energy out at the end. So B and C have that order for us. So we're getting chemical energy from the coal. We are heating the water to turn it into steam, and that steam is then driving the turbine. So we're getting chemical, we're generating thermal energy to heat the water, turning that into steam, kinetic, spinning the turbine, and then getting electrical out at the end. The answer is B. 20, a black body 1 meter squared emits EM radiation. We've got peak wavelength 2.9 times 10 to minus 6 meters. Which of the following statements are correct? The temperature of the body is 1,000 kilograms, 1,000 Kelvin even, not kilograms, 1,000 Kelvin. So this is coming from our lambda max T equals a constant, equals 2.9 times 10 to the minus 3. So T is 2.9 times 10 to the minus 3. We rearrange this, divided by lambda max, which is very conveniently also a 2.9, but a different power of 10. It is 2.9 times 10 to the minus 6. So it is 1 times 10 to the 3 Kelvin, or 1,000 Kelvin. That is correct. The energy radiated in 1 second is 5.7 times 10 to the 4. Energy radiated 1 second is the power. The power that we're getting, going to our data booklet, the power is the emissivity divided by multiplied by Stefan's constant times the surface area times the temperature to the power 4. It's a black body, so the emissivity is 1. So that is 1. Stefan's constant, we look that up in our data booklet, it's 5.67 times 10 to the minus 8. They're told the surface is 1 meter squared, so the surface area is 1. We've established that the temperature is 1,000 Kelvin, so 1 times 10 to the 3 to the power 4. That comes out to, simplified down, 5.67 times 10 to the minus 8, Stefan's constant, multiplied by, and then that ends up being 1 times 10 to the 12 from the 10 to the 3 to the power 4. That gives us 5.67 times 10 to the 4 watts, which is 5.7 times 10 to the 4 watts, which is joules per second. So 2 is also correct. The body is a perfect absorber of EM radiation. That is also true. That's part of the definition of what makes something a black body, is a perfect emitter and absorber of all wavelengths of EM radiation. So 1, 2 and 3 are all correct here. Question 21. This looks like it's going to be a bit of SHM. Mass on a spring is extended beyond its equilibrium length, executes simple harmonic motion. Which of the following is independent of the initial displacement? So the initial displacement of the spring is going to be x0. It's going to be the amplitude of the motion. Go to the data booklet. Let's look at the equations. Angular frequency, that is omega equals 2 pi over t. That does not depend on x0. Let's have a look at B, C and D. If we look at the equation for total energy, that does have an x0 term. It's not that one. Speed, we don't have an equation specifically for average speed, but all the speed equations all depend on x0. The speed of the mass depends on where it is in the oscillation. The maximum kinetic energy, the kinetic energy equation, also depends on where it is in the oscillation, so only A is independent of the initial displacement of the spring. It's the only one without x0 in its equation. Single slit diffraction, light of different colours. The width of the central peak is measured. What is the order of the colours that correspond to increasing width of the central peak? So our single slit equation is this one, theta equals lambda over b from our data booklet. It's the angle to the first minimum. So if we think about kind of the single slit pattern, it's the angle to this first minimum. So the width of the central peak divided by 2. So if we look at that expression for the same slit, so for the same b, if we have a larger wavelength, so as lambda is larger, theta will be larger, and if theta is larger, we're getting a wider central peak. Red has the largest wavelength, so it will have the widest central peak. Blue has the smallest wavelength, it will have the narrowest central peak. Green will be in the middle. The answer is C. Question 23, we've now got a double slit, so we've got the interference pattern. The distance between the slits is d, what can be deduced about the ratio lambda over d, and the effect of single slit diffraction in this experiment. So have a look at the options. So single slit diffraction, non-negligible or negligible. Basically, can we see the effects of single slit diffraction or can we not? Yes, we can see the effects of the single slit diffraction. We can see the single slit diffraction envelope clearly evident here. That is non-negligible. We can definitely see that. So we're going A or B, and then we're after what is lambda over d. So if we look at our data booklet for our diffraction equation, we get n lambda equals d sine theta. And let's look to the first order diffraction patterns. Let's look to the first order. So the first order fringe is here at an angle of 0.01 radians. That's its diffraction angle to the first order. So let's make n 1, looking at the first order. Lambda is lambda. D is d sine theta. So lambda over d equals sine theta. Now, when theta is in radians and the angles are very small, 0.01 radians is a very small angle, we can use the small angle approximation where sine theta is approximately equal to theta. So we can get rid of the sine and we say basically lambda over d is equal to theta, which for this first order maxima was 0.01, making the answer B. Simple pendulum, mass and length, period of oscillation is t. What is the period when we have mass 4m and length 0.25 L? So this is write out an original algebraic expression, write out the new algebraic expression, try to factorise out your original expression with your multiplying factor at the front. So originally our initial scenario is time period equals 2 pi root L over G is the equation from our data booklet. Let's then consider the new scenario. T new is now 2 pi root, and we've now got 0.25 L over G. So I want to try and factorise out 2 pi root L over G again. So take the 0.25 out, well, the square root of 0.25, the square root of 0.25 is 0.5, so this becomes 0.5 multiplied by 2 pi root L over G. There is my original expression for T. I now have a value that is 0.5 times that. The answer is A. The mass is irrelevant. It does not affect the time period of a pendulum. Question 25. Train at constant speed emitting a sound wave of frequency f0. At t0, the train passes through a station. Which graph shows the variation with time of the frequency f of the sound as measured by an observer standing on the station platform? Doppler effect. So as the train approaches, they're going to hear a higher pitch on approach, then a lower pitch as it moves past them. So B can go. The observer definitely notices a change in the frequency. C can also go because when the train goes through the station at time t0, they are going to hear the actual frequency of the wave, which C does not accomplish. Then it's just a question of whether we're going for A or B. So A is showing the pitch increasing on its way into the station, then decreasing, then increasing again on its way out of the station. That is not what we see. We see a higher pitch on the approach. We then hear the actual frequency as it passes the observer, and then we hear a lower frequency as it moves further away. And the answer is D. Question 26. We've got a negative charge moving in an electric field. We've got some equipotential lines. 4 possible paths, which shows the largest work done. So if we go to our data booklet, we'll see that the work done is equal to Q multiplied by the change in potential. It is a negative charge that we're dealing with. We're dealing with a negative Q. So in order for the field to do the work, the field will be moving that charge towards a more positive potential. It will be moving it from negative to positive if the field is doing work. So we need a path where the potential is getting larger, is going to a more positive value. So A and D are out. B and C show the particle moving from a lower potential 10 volts up to a higher potential 20 or 30. That is the field doing the work. Then to get the largest work done, we need the largest change in potential, and that is B. Question 27, we've got an oil droplet, mass M, charge Q, 2 horizontal parallel plates. The electric field between the plates can be adjusted. Air resistance is negligible. What is correct when the droplet falls vertically at constant velocity? So if it's moving at a constant velocity, then the resultant force acting on it must be 0. So if we think about the oil droplet in the middle, we have its weight pulling it down. In order to get a resultant force of 0, we must then need the force from the field to be acting vertically upwards in order to give us a 0 resultant force. So if we think about our two equations, the force from an electric field is equal to E times Q from our data booklet. Weight is equal to mg. So we've got mg is equal to E times Q. A rearrangement of that would be E equals mg over Q. The answer is C. Question 28, we've got a satellite orbiting a planet. Which graph shows kinetic energy, potential energy, and total energy varying with distance? So again, go and check your data booklet for your equations. So potential energy is minus GMM over R. So potential energy is negative. A can go. Potential energy is not positive for gravitational fields. The kinetic energy for a gravitational field, kinetic energy is a half v squared, but then we know for an orbit that v is equal to root gm over r. If we sub that in, that gives us kinetic energy equal to a half, and then we're going to have the square root's going to go, it's going to be gm over r. That is a positive value, so C can go because that is showing a negative kinetic energy. It's definitely a positive kinetic energy. Then as for the total energy, we've got B and D remaining. Is the total energy less negative or more negative than the potential energy? So the total energy is the kinetic plus the potential. So that is the kinetic half g over r, and then the potential energy is negative, so minus g over r. So this is a half minus a whole, so that is minus a half g over r. So the total energy is indeed negative, but if the potential energy is minus 1 gmm over r, the total energy is minus a half gmm over r. So the potential energy is more negative than the total energy. Basically, we've got a negative plus a positive, giving us slightly less of a negative, so it is B. Question 29, we've got a coil rotating inside a magnetic field at a constant angular speed. What is the EMF between X and Y? So for an EMF to be induced, we need there to be a changing flux within the area of the coil, so within this section. Now that's where we need to do a little bit of visualizing. If I spin that axis and that coil rotates, the magnetic field that is shown does not pass through this area at all. It is not moving through that area of the coil. There will be no changing flux through that area. If I wanted that field to pass through a coil, the coil would need to be this orientation. We would need to have it here. We need the field to be passing through the inside area of the coil, which it will on this one, it will not on that one. Those field lines are not going to go through that area. Even if it becomes vertical, they're still not going to go through. The field would need to be going in this direction in order for it to pass through the area. So there is no EMF induced as that coil rotates at all, as the field never passes through the area inside the coil. Question 30, we've got a conducting rod being moved. We've got field B, the field's at right angles to the plane of the paper, so either into or out of the page, that's fine. We've then got the rod, length L, moving at speed V. What is the power required to move the rod? It's connected to a resistor of value R. So the EMF that would be induced in that rod would be V times L from our data booklet. It's moving at a constant speed. We're after the power required to move the rod. Now the power required to move the rod should be the same as the power dissipated by the resistor R, just from an energy conservation standpoint. The energy put in is the same as the energy that comes out. So the energy put into generating the current is the same as the energy the current produces as it moves through the resistor. So the power of the resistor is going to be V squared over R, where V is our EMF that we induce by moving the rod. So our power is the BL all squared over R. So B squared, V squared, L squared over R, which is C. Question 31, AC power supply, EMF with peak amplitude V0, delivers an average power. What is the root mean squared current delivered by the supply? So the average power is equal to the root mean squared current. multiplied by the root mean squared voltage. Check your datasheet, root mean squared voltage, because we are given the peak amplitude of the voltage V0 is V0 divided by root 2. Sub that into the expression, and our RMS, we then got V0 over root 2. Little rearrangement, it's P multiplied by the root 2 divided by V0 is our RMS, which is C. Question 32, four-wave diode rectification circuit. We've got an addition of a capacitor. It's rectifying a sinusoidal signal with a period of 6.3 milliseconds, which graph shows that the potential V varies with the load with time. Now, the point of adding a capacitor is that it smooths the signal. C and B do not show this smoothing, so they are out of the question. It is A or D. That's the whole point of the capacitor. It gets rid of this kind of up, down and gaps. We get a smoothing. It doesn't drop off as intensely in between, so it gets closer to a direct voltage. The sinusoidal signal has a period of 6.3 seconds. So if we think about the graph, we've got a sinusoidal signal. So kind of two sections of this graph are going to be the time period of the sinusoidal wave. So we're kind of looking at the graph, and D has a time period that's way too large. A has a time period that's much more in line with the 6.3 milliseconds. The answer is A. We're smoothing out both the positive and the negative on the sinusoidal signal in the 6.3 milliseconds. Parallel plate capacitor, question 33. Constant EMF. Plates are then moved further apart without disconnecting. What are the changes in the field and the capacitance? So looking at the datasheet, the field between parallel plates is equal to V over D. So if we increase the separation of the plates, we're going to drop the strength of the electric field. The EMF is staying constant throughout. The cell is never deconnected, so V stays constant. So E is decreasing, and then capacitance is epsilon A over D. So epsilon hasn't changed. We've not changed what's in between the plates. The area of the plates hasn't changed. There's the separation. Again, the separation's been made larger, so therefore the capacitance will drop. The answer is D. Question 34, we've got three capacitors. What is the total capacitance? So again, go to your data sheet. When we have capacitors in series, like we do up here at the top, we do 1 over the capacitance in series is equal to 1 over the capacitance plus 1 over the capacitance. So 1 over CS is then 2 over C. Flip both sides. So in series, we have a total capacitance of C over 2 along the top section. We've then got that in parallel with another capacitor C. When they're in parallel, we just add them together. So those in parallel is C2, the two series ones, plus C for the parallel one. So that is 3C over 2. The answer is C. Question 35, which of the following experiments provides evidence for the existence of matter waves? So matter waves, that is particles behaving as waves. So particles behaving as waves. So which of these is an example of particles behaving as waves? Scattering of alpha particles, no, that's just particles being particles. Electron diffraction, diffraction is a wave property. Gamma decay, that is just a wave, nothing to do with particles there. Photoelectric effect, no, that is evidence for waves behaving like particles, the photon being a packet, a particle-like version of a wave interacting with the electron. So no, the answer is B, electron diffraction. That is a particle behaving like a wave. Question 36. We've got variation with distance x of the square of the amplitude of the wave function of a particle. Which graph corresponds to a particle with the largest uncertainty in momentum? So this is Heisenberg's uncertainty principle. The more certain we are about the position of a particle, the less certain we are about its momentum. Okay, so that is this expression here from our data sheet, delta x, delta p, greater than or equal to h over 4 pi. So the more certain we are about x, the less certain we are about the momentum. So if we look at these four graphs, graph D has the smallest range for where the particle could be located. Remember, the square of the amplitude of the wave function is the probability of finding the particle in that place. So we've got a very high probability up here of finding it in a very small region of space. So we are very certain about where it is, but then according to the uncertainty principle, if we're very certain about where it is, we're very uncertain about its momentum. So the answer is D. Deviations from Rutherford scattering, question 37, are detected in experiments carried out at high energies. What can be deduced from these deviations? So these deviations, this is the alpha particle scattering experiment, they are evidence for the existence of the strong nuclear force. So it's a bit of a knowledge question. So evidence for the existence of the strong nuclear force. So impact parameter of the collision, no. The existence of a force different from electrostatic repulsion, yes. The size of the alpha particles, no. The electric field inside the nucleus, no. The answer is B. It was evidence for another force, the strong nuclear force, that was not the electrostatic repulsion force that they were aware of already. Question 38. Different metal surfaces are investigated in the photoelectric effect. A graph of the variation of maximum kinetic energy with frequency is drawn for each metal. Which statement is correct? So that is this graph, which we should be familiar with. So the variation in kinetic energy with frequency, it's linear. It crosses the x-axis at the threshold frequency. All graphs have the same intercept on the frequency axis. No, the threshold frequency f0 is dependent on the metal. So different metals will have a different value for f0, so that is not correct. Work function is the same for all surfaces. That is also not correct. So work function is down here. It is the y-axis intercept. No, they don't all have the same work function. Different metals have different work functions. It's not the same for all surfaces. All graphs have the same slope. That is true. You may already have that just as knowledge. I'll show you the equation in a sec that proves that. The threshold frequency is the same for all surfaces. No, different surfaces have a different threshold frequency. Different metals have a different threshold frequency. So the equation we're dealing with here is this one. The maximum kinetic energy is equal to HF minus psi minus our work function, and that's lining up with our equation for a straight line. So this is plotted on the y, mx plus c. Frequencies on the x-axis, that makes the gradient h, which is Planck's constant, so every graph has the same gradient equal to Planck's constant, and then the y-axis intercept is equal to the work function, so c, all graphs do have the same slope, is equal to h, Planck's constant. Question 39. A pure sample, mass m, of a radioactive substance with half-life T1/2, initial activity A0. What are the half-life and the initial activity of a pure sample? The same radioactive substance, but it now has a mass 2m. Well, if it's the same radioactive substance, it has the same half-life. It's the same isotope, so it's A or B, the half-life's the same. Then the initial activity from our data sheet is this expression, lambda m0 e to the minus lambda t. The initial activity is dependent on the number of radioactive nuclei. So if we've got twice the mass of the sample, we're going to have twice the number of radioactive nuclei, and therefore we're going to have twice the initial activity. The answer is B. Finally, question 40. Nuclear density, which sentence is correct, is constant because volume is proportional to nucleon number, is constant because volume is proportional to proton number, depends on the nucleon number, depends on the proton number. So density is mass over volume. Now the mass of the nucleus is given by the mass number, A, multiplied by the unified atomic mass unit, U. The volume is 4/3 pi r cubed, and for the nucleus, R is equal to R0 times A to the third. So R0 is a constant, A is the mass number again. So we're going to have density equals AU over 4/3 pi. We're cubing all of this expression. So we're going to have R0 cubed and then A to the third is just going to become A. The mass number or the nucleon number is going to go. And we're going to get left with U over 4/3 pi R0 cubed, which is our constant density. So the density of a nucleus is constant. It's just dependent on U, which is a constant value, 4/3 and pi, which are all constant values, and then R0, which is a constant value, being cubed. So nuclear density is constant, so it's not C or D. And it is constant because the volume is proportional to the nucleon number. A is the nucleon number, the mass number. The answer is A. And we are at the end of the paper. I hope that you found that useful, and as ever, best of luck with your ongoing revision.